Let's walk through the process of finding forces and torques on current-carrying wires using integration. I have here a segment of wire of length big L, carrying current I, flowing downwards. It's pinned down at the origin and free to rotate about that point in the XY plane. There's a non-uniform B field pointing out of the page, which is the positive k-hat direction. The B goes like some constant c times y squared. Having drawn a diagram, the next step is to write down our basic equations. Now, I can't use F equals IL cross B for more than qualitative reasoning, since B is non-uniform. But I can use it to rough out some expectations. Crossing the direction of the current flow with the direction of the B field, I get a force that points to the left. And based on that and the location of the pivot, I should expect some counterclockwise torque. As I go through the problem, I'll check my answers against these expectations. Anywho, to find the total force on this wire that comes from that non-uniform B field, we start from the expression for differential force. A little bit of force dF comes from a little bit of wire dL. And the dL points in the direction of the current flow. It's a little chunk of length in the y direction, oriented downwards. So we write it as minus dyj hat. Now I cross that with my B, and j cross k is I. So that's our differential force dF. To get the total force, we integrate up all the little dFs as so. We're integrating with respect to y, and the wire begins at y equals 0 and ends at y equals L. So I put in that information and crank it out. And that's our force. It's in the negative I-hat direction, which is to the left, as expected. Now, given that there's a force on the wire and the wire is free to rotate, it's likely that there'll be some torque too. Let's figure that out. Oftentimes when people are doing problems like this one, they're tempted to say, well, torque is R cross F, and we just calculated F, so can't we just cross it with some R? But that's not going to work. R is the displacement vector pointing from the pivot to the point at which force is applied. And there are many forces being applied at many different R's, one for each dL. To solve this, we have to wind things all the way back to the differential definition of torque. d tau is R cross dF, and we know the dF is I dL cross B. We have to completely calculate d tau before we integrate it, which means we have the nested cross product. Fortunately, we did calculate dF in the last part, so I'll pull that forward. As I said, R points from the pivot, the origin, to the place where force is applied, the location of the dL. That vector is of variable length along the y-axis and is upwards. So I'll write it as positive yj hat. Then I cross it all out to get d tau. And I integrate up all the bits to get total torque. We're integrating with respect to y, and the bounds again go from 0 to L. And there's our answer. It's a torque in the positive k-hat direction. You may recall from mechanics that we use the right-hand rule to relate the direction of a torque vector to the sense of rotation. I stick my thumb in the direction of the torque vector, and I curl my fingers around, and that is a counterclockwise torque, like we hoped. Summing up, these problems aren't too disastrous if you make sure you work from fundamental equations and you lean heavily on your diagrams. The most tempting mistake is usually to try to use your F to calculate tau. But remember, if you have a distributed force, like this one, you're probably going to have to roll all the way back to d tau. And once you've done that, there's a decent chance it'll all work out.